Okay guys, just about time. How's everybody doing? Our usual silent classroom. I'm feeling a little quiet today too. So we'll see how that translates into class. All right. Andrew, I see he's not here. Has anybody seen or heard of Andrew today? No? Whose turn was it to keep track of it? Nobody? Okay. And let's see. Jay. Anthony is here. Jonathan. Caleb. Anybody seen Caleb today? No? All right. Zachary. Here. Lucas. Anyone seen Lucas today? Caitlin is here. Matthew.
Great.
You, Dylan.
Here.
There's Andrew.
Andrew Garner.
Yep. I'm wondering where you were. Mike. Edvard. Did I see Edvard today? No? See, I'm going to have to assign people to watch other people. No, that sounds a little creepy, doesn't it? Yeah. Jason is online. Okay, good. All right, guys. So I posted all of the grades for the test. They're on Canvas, so you should all have seen that. If you took it in person, you're going to get your copy back today. If you did not take it in person, there are some comments up on Canvas that you can take a look at. I'll probably speak a little bit to the questions today, but I'm not going to go over specific solutions. If you have specific questions on something, please contact me and we'll try and make everything clear for you, okay? Yes? No? All good. All right. So, first thing I want to talk about is the homework that was assigned. You guys remember that? It kind of looks like what's on the screen now with some labels on there. And just to remind us of what it was, I'll throw some dimensions up. We have a wow, that's a little large. I guess we did it. 2-inch long crank and a 3.7-inch long conrod. And what we wanted to do was figure out what the velocities looked like around this thing. And then maybe we'll talk a little bit about the accelerations, right? So here's the crank, it ends right there. And we said that this was rotating at 10 radians per second, right? And we didn't say whether that was positive or negative, so we're going to assume positive. If that's the case, it's 10 radians per second, and we're calling it positive, then what we need to do to show the velocity of point A is draw a line. It's going to be 10 times 2, so 20. And to scale then, this green line is our velocity vector for point A. Make sense so far? Okay. The next thing we would want to do is draw the velocity vector of B with respect to A, right? And what direction is it, by the way? Perpendicular to the straight line between those points. So if I highlight that line, do that, it's perpendicular to that little line down there. Good so far? Okay. And it starts at the end of velocity vector A. Yes? Okay. So here's where it gets kind of fun. We also know that we're going to have a velocity vector for point B, the point down here at the end. And it's constrained to be horizontal, right? But at top dead center and bottom dead center, the velocity of the piston is 0. So that means that our velocity vector for B goes from the end here back down to there. So the magnitudes of the velocity vector for the velocity of point A and for the velocity of B with respect to A are identical. Make sense? Now, if we talk about this from a graphical acceleration point of view, what does it mean?
So, in the acceleration, there is tangential and normal acceleration.
Correct.
The normal will be to the center, like to the center of the motion, and tangential will be perpendicular.
Correct.
So, one is the flow, and the other is tangential.
So let's do a little quick exercise here. And let's say that we wanted to create our table of accelerations. So we would start with the acceleration of point A, and it'd be the normal. Sorry, I can't do a really pretty one with this. And we know that its magnitude would be equal to what? Omega 2 squared multiplied by the length of the conrod. Does that look vaguely familiar from Monday? Okay. And we know that it would be from point A to our center of rotation, O2. The tangential acceleration of point A is equal to alpha 2 multiplied by L2. And that is perpendicular to L2. So far, so good? The normal acceleration of B with respect to A would be omega 3 squared multiplied by L3 from B to A. And the tangential acceleration of B would be alpha 3 multiplied by L3 perpendicular to L3. And then we have some acceleration of B. Now, we know that this conrod is, or excuse me, the crank is 2 inches in length, right? And omega 2 is 10 radians per second.
So it's 200.
So it'd be 200. Just like the first problem we looked at using these dimensions. As long as omega isn't changing and the crank length isn't changing, that's going to be the same. Which does, by the way, I keep going into these little sidebars, sorry. Has anybody heard of variable compression ratio engines? So think about that a little bit, about what that does to the accelerations as you change these lengths. Kind of an interesting problem. All right. We weren't given an acceleration, an angular acceleration for this. So that's still 0. Omega 3, if you recall, these two vectors are the same length. So we said that the length of the normal acceleration of A is 200. So that means that the normal acceleration of B with respect to A is also 200. But the angular velocity would be different, right? B is equal to omega r. So that means that omega 3 is going to be equal to 200 divided by 3.76. Does that ring any bells? Seem to make sense? 53.2. So 53.2 squared multiplied by 3.76 says that our acceleration of B with respect to A is actually pretty high, 10,641. All of a sudden, it got really big, right? We don't know alpha 3. We're going to have to draw the acceleration polygon to find out. And of course, we don't know the acceleration of piston. We'll put that over there. Now, if we're going to draw this, the acceleration for this is going to be kind of interesting, right? Because we're going to have this first line that we said is 200. 200. Zoom out. See how that looks in relation to the device, right? And then we're going to have the next line, 10,640. I don't think I'll draw that one. We won't be able to see anything else. And remember, it's going in the same direction. So the acceleration of the piston then, or excuse me, yeah, the acceleration of the piston and the acceleration of the conrod have to get us back to where we were. So what this should be lighting off as alarm bells in your head is, in this kind of a mechanism, the accelerations at top dead center and bottom dead center are huge. This is why engine designers make such a big deal about lightweight pistons, lightweight conrods, right? Making sure that side forces are reacted properly, because these things undergo just massive accelerations. Kind of neat. Think about that when you're driving home today. Any questions?
So the acceleration.
Bashar, you have to speak up, I'm sorry.
The acceleration for point A, the tangential one, will be perpendicular on the acceleration A normal.
It would be perpendicular, but remember that the acceleration needs to make a closed loop.
Yeah.
So since there is no other perpendicular component,
Yeah.
There is no
So in this case,
tangential
the
acceleration.
acceleration will be inside the point, inside the point.
It will just be horizontal. And it's gigantic. 10,841 for this particular, 10,841. Now this actually leads me to maybe an interesting question. How much does a piston weigh, guys? It does. I mean, a normal weight for an aluminum piston is probably what? Half a pound? That's probably a little on the low side. So, just for giggles, force is equal to mass times acceleration. And if we want to get this 10,841.7 divided by 12, 903 feet per second squared. And that times 0.5, 450. Wow, that's a lot of force. Off one piston. Now remember, this is only kinematic. The stuff being generated by kinematics. This is completely aside of whatever you're getting by exploding fuel in the engine. A lot of force. Okay. Well, that's good. That warms up the discussion a little bit. And let's see. Caleb? No, who came in? Lucas came in. Oh, I'm sorry. Thank you, Edward. Hooray. All right. So, what we said we were going to do last time was look at sample problem 7.2. This is on page 368 in your book. So let's do that. Sample problem 7.2. Get to it and see what it looks like. There we go. So I can draw a little sketch. I just need to get to it for a second, guys. Hold on. Alright, so we've got a 4-bar link, and it's going to look something like this. Our fixed length is about 100, our crank is 40, and it's at an angle of 40. Our pound connector is 120, so it's actually pretty long. And our rocker is about 80. So it kind of looks like this. And that's just labeled, guys, with D for our fixed length, or L1, A, B, and C. It's following the normal book nomenclature, confusing as it is. If we were to check this, we'd find that this is a Grashof linkage. Specifically, it's a crank rocker. For a crank rocker, that says that the crank is always the shortest. Okay? Now, as we know, if we're trying to do an acceleration analysis for something like this, we must have already done the position analysis and the velocity analysis. So in this case, we've got a couple of things. We know, I'm trying to write this big initially, that theta 2 is 40 degrees. Hopefully the camera is picking that up okay. That theta 3 is 20.3 degrees. And that theta 4 is 57.3. So we have our position. We also have velocities. Omega 2 is given to us as 25 radians per second. And way back in chapter 4, this is from example 4-1 in chapter 4. No, I'm sorry, this is chapter 6. Example 6-7. We found that omega 3 is equal to negative 4.1 radians per second. And that omega 4 is equal to 7 radians per second. And what we want to do is find alpha 3 and alpha 4. We also wanted to find the acceleration of point A, which is right here. The acceleration of point B with respect to A. And we want to find the acceleration of point B with respect to our fixed reference frame. That's a lot to do, isn't it? So I hope you all have your calculators out and we can take a stab at this. Now, if you were to take a look at the notes from last class, you'll find that all of the equations to do this have been collected on those sheets. I will urge you guys to practice this. Practice it here in class. Practice it at home with the homework. Because all of these intermediate calculations are very tedious and they don't really fall into something that is easily recognizable or something that you can have correspond to the physical situation. So it's very easy to screw them up, even though they're simple enough calculations. So, we have a number of things that we need to calculate. Get to that same sheet, so I've got the same notes to work with. And we've got the following intermediate calculations to put together. First, we have to find a factor called A. And A is equal to the length C multiplied by the sine of theta sub 4. So, let's see, our length C is the coupler length, and theta sub 4 is given in a problem like this. It's this angle. So this is pretty easy to figure out, right? That's good. Where are your calculators? 57.3.
Oh, so what's the length for C?
I'm sorry, I guess I didn't write that down. Oh, I said it. I didn't write it down.
Yeah.
My problem. My bad, guys. So, this is 40 millimeters, 120 millimeters, and 80 millimeters. So C is 80 millimeters.
So 67.3.
67.3, yes. Next factor, also simple. B, this is equal to B multiplied by the sine of theta sub 3. What do you do to the Bashar this time? Spread the wealth. Yes. Then we have another really fun one. C. Our C intermediate factor is a little bit more involved. So this is A multiplied by alpha 2, which I have to give you, multiplied by the sine of theta sub 2, plus A multiplied by omega sub 2 squared multiplied by the cosine of theta sub 2 plus B multiplied by omega sub 3 squared multiplied by the cosine of theta sub 3 minus C multiplied by omega 4 squared and the sine of theta 4. So it does say that we need to know alpha 2. I should have written that down. Alpha 2 is given to us as 15 radians per second squared. Now, as we look at these factors, some things can kind of grab us, right? We can certainly look at factor A and B. Those are definitely geometric factors. We can look at factor C, and we see that we have an alpha times a length and an omega squared times a length. So that definitely has something to do with the tangential accelerations and the normal accelerations. But unfortunately, those intermediates are not directly something that we can pick up and say this is equal to just one thing. Still, let's go ahead and calculate a value for C. Anybody get one? Slowly, exactly. And this is why, guys, it really behooves you to have a little practice. I don't know if anybody ever uses the word behooves outside of a classroom, do they? How are we doing online, guys? Timothy, I see you kind of coming up, but I don't see any sound. Mine's turned up. Anybody else awake online? Well, I see some things, but I'm not able to hear you. Still, kind of looks like you're around. $20,870?
Yeah.
Anybody else get something different? I got something a little different.
18,129.
I got 19,310. So, what's that going to mean? Well, unfortunately for these intermediate calculations, you get them pretty close for this to work. I'm pretty sure that I got it right. 19,310.95. And I see at least one person in the classroom got the same thing. Anybody else? Okay, close enough. Really neat, isn't it? This is why I like the graphical technique. All right. So now that we have that, we actually have 3 more things that we need to calculate. So let's do that. We have a factor called d, which is equal to c times the cosine of theta 4. E, which is equal to b times the cosine of theta 3. Get some values for those. Yep. We'll give it a 43.2.
And E is 112.54.
Yep. 112. I'll give it 112.6. Close enough for now. And then we have another one of these long equations. So I'm going to erase the equation for C so that we can get the equation for F fit in. I just want to make sure that I don't erase our value. Get that transferred up. And I'm kind of holding myself to a small section of the board, guys, so that we can try and fit this all into the camera. All right. So the last one that we need to get, of the intermediate calculations at least, is called F. And F is equal to A multiplied by alpha 2 multiplied by the cosine of theta 2 minus A times omega 2 squared multiplied by the sine of theta 2 minus B multiplied by omega 3 squared multiplied by the sine of theta 3 plus C multiplied by omega 4 squared multiplied by sine of theta 4 Okay. So let's see if we can get that. Negative 13,011? Yes. So F is negative 13,011.2, roughly speaking. Okay, now that we've gone through the great fun of calculating all those intermediate values, we can actually do a little plug and chugging in order to get alpha 3 and alpha 4. Alpha 3 is equal to the following. C multiplied by D minus A multiplied by F divided by A multiplied by E minus B multiplied by D. You can see why this method requires intermediate calculations. You tried to plug everything in for that. You'd be off. Anybody getting alpha 3 yet? $296.1. What are the units, Kate?
Millimeters per second squared? No, radians per second.
Radians per second squared. Great. 296.1. Okay, so that's alpha 3. Alpha 4 is a similar calculation. And this is equal to C multiplied by E minus B multiplied by F divided by A multiplied by E minus B multiplied by D. $469.9. I'm sorry, Chuck? 469.9 radians per second squared? Yes. Whew. It's a lot of work, isn't it? The best part is we haven't yet figured out the accelerations of point A and B. So, for homework, guys, since we're coming up on a weekend, right? Who's going out and having fun on the weekend? Nobody? Yes? Okay, so in order to keep Andrew safe, I'm assigning homework. Not too much. Please, ladies and gentlemen, take this information and calculate for me the accelerations for point A and B based on the equations on page 13 of Monday's notes. Okay? So that's finishing up this example problem.
Repeat that.
Yes. I want you to finish example problem 7-2 by finding the accelerations for points A and B per the equations on slide 13 of Monday's notes. Okay? Now, one other thing, perhaps, well, actually you guys probably won't be interested, but I think it's kind of fun. This is how we solve this kind of problem analytically. And it's not terribly hard, but it does require quite a few intermediate calculation steps. And as we all found out as we were running through these, there's ample opportunity to make mistakes. When I did this graphically, here are the numbers that I got for alpha 3 and alpha 4. And bear in mind, I think I did this manually. It's on a piece of paper. For alpha 3, I got 295.8. Radians per second squared. For alpha sub 4, I got 469.7 radians per second squared. With something that you can do with a ruler and a piece of paper and a pencil. Pretty easy. So, who wants an extra credit opportunity? All right. Your extra credit opportunity is as follows. I will post this. I'll post both of these, at least up on Canvas, so you remember what the assignments are. Using this linkage from example 7-2, perform a graphical acceleration analysis and tell me alpha 3 and alpha 4. I want to see your drawing, okay? So you are welcome to bring it in on Monday as a piece of paper for extra credit, or you can post it up onto Canvas. I will create the extra credit assignment, and we'll go from there. All right? Questions? Overwhelming? A little bit. That's why you're practicing, guys. All right. Let's get into this evening's notes, because I know you want more to talk about. Besides, who is this jerk that's up here teaching this stuff? Oh, we're going to talk about jerk tonight. So, tonight we're going to be covering sections 7.3, 7.4, and 7.5. Please note that I would like you to take a stab at reading through section 7.6 and 7.7 on your own. I probably won't, no, I shouldn't say probably. I won't test you on the material in those sections, but I think you'll find it interesting. It talks about human tolerance for acceleration, which is kind of cool. And it talks about the next derivative of acceleration, which is called jerk. So those are worth having as concepts, at least in your head. So analytical solutions for accelerations. Continuing on with what we talked about. We looked at a 4-bar link, particularly a crank rocker. If we look at something like a crank slider, and remember a crank slider, this should be probably called this is a crank slider. That means that we're driving the crank. We can do exactly the same kind of analysis that we did with the previous one. That derivation is in your book if you want to take a look at it. It's not necessary to do so. What it boils down to is that if we know the position and the velocity, we can differentiate in order to get an expression for acceleration. And this is again using that Euler identity so that we can split up between the accelerations that are in the x-axis on plane and the accelerations in y, since they're independent. We can then do some simplification, make things a little prettier, and come up with a way to calculate alpha 3 based on that information. Because this is a crank slider, it's a little bit, I guess, simpler than that crank rocker. We don't need to go through all of the individual intermediate calculations. It simplifies down to something that's a little bit more manageable. Same thing with the acceleration of the piston for this mechanism. There is an example 7-3. It's on page 371. Who's shell-shocked? Anybody shell-shocked by going through example problems? No? We love going through example problems? Really? That's awesome. Let's do one. This is going to be the most fun I've had all day. All right. So this is what we've got. This actually follows, if you want to reference it, example problems 4-2 and 6-8 in your book. That's to get the position and the velocity. And we're given the following. L sub 2, which we often call A, is 40 millimeters. L sub 3, we often call B, is 120 millimeters. And L sub, why do I have two of those? Let's see. L sub 4, C, is -20. So this is an offset crank slider or slider crank mechanism. We're told that theta 2 is 60 degrees. That omega sub 2 is -30 radians per second. And that alpha sub 2 is 20 radians per second squared. And from these previous problems, we found out the following. Theta sub 3 is equal to 152.9 degrees. omega sub 3 is equal to 5.6 radians per second. And we can kind of draw this thing. I draw it over here, and I might have to erase it. Sorry, camera. We'll look at something like this. This is that 20 millimeter dimension. We are also given the position D of the piston, and it's at 126.8 millimeters. All right. So what we want to do is find alpha 3 first, and then we want to find the acceleration of the piston. So alpha 3 has that fun, neat equation. I'm going to throw the slide back up momentarily, and then we'll go back to this. It's in your notes. This is the equation that we can use to solve for alpha 3. Pretty simple. And because this simplifies so well, this one's truly just a plug and chug. Should I write down the equation, or is everybody looking at it in their notes? Some of you are looking at it in your notes. Okay, so let's go ahead and try that out, see what we get. Really nice class before us gets out a little early. Timothy, I'm not sure when you did this. Oh, it looks like it was a few minutes ago. Can I repeat that equation? I'm afraid not. It is in the notes from Monday or today. What did you get, Chuck? 272? Yes. So, alpha 3, 272 radians per second squared. So this, in comparison to a crank rocker, pretty easy, right? The equation for calculating the acceleration of the piston is similarly simple. So I don't think we'll need to sit through that. I would suggest, guys, that you take a look This is, as I said, example problem 7-3. Do try the equation, just for your own education. All right. For the opposite kind of problem, slider crank, we can calculate alpha 2 and alpha 3 if we are given the acceleration of d. This is the next slide. This also has an example problem. It is similarly simple to the example that we just did, so I won't take class time going through this one, okay? But these are all pretty easy for the crank slider and slider crank. All right, let's talk about something else. So we've talked about normal acceleration and tangential acceleration. There is a third acceleration that we generally don't deal with a whole lot in mechanical engineering, although it does come up depending on your kind of problem. You actually hear about this more in a completely different field of science. Anybody hear of Coriolis acceleration before? And where did you hear about it? That's okay. That's okay. Coriolis acceleration is the acceleration that you get from calculating things in a rotating frame of reference. So if we, I think I wrote down, maybe I didn't. The definition on this is like poetry, if you like this sort of thing. I'm not sure if I wrote it down. Probably didn't. What's that? It is obviously from physics, but where you end up seeing Coriolis acceleration more often than not is in meteorology. Because Coriolis acceleration is what gives hurricanes their spin. So, if you have, in a mechanical engineering point of frame, if you have a link that's sliding along some kind of rotating member, then we have this fictitious acceleration called Coriolis. I say fictitious, but it does have an effect. We do have to account for it if we have that rotating frame of reference. So it occurs in situations like this, where I have a rotating point, or excuse me, a point, a link that's rotating, and this sliding piece. One way that you can experience Coriolis acceleration, and you probably have, is if you're on a and you walk either from the outer edge towards the inner or the inner towards the outer, you kind of get pushed sideways as you're walking. Anybody ever experienced something like that? That's Coriolis acceleration. So, when we look at a situation like this, acceleration of a point on that slider is going to consist of the normal and tangential of some coinciding point on the rotating link, if we're trying to calculate. Plus, we're going to have a relative acceleration of the slider along that rotating link, plus the Coriolis acceleration. The magnitude of the Coriolis acceleration comes from this vector cross product. We can calculate it as 2 times omega times the velocity of that slider with respect to the link. For planar linkages like this, we can find the direction of the Coriolis acceleration by rotating the relative velocity vector between the sliding link and the rotating link 90 degrees in the direction of the rotating path. So, if this link is rotating clockwise, we can rotate that relative velocity with the slider going this way 90 degrees into the path. This is the direction that the Coriolis acceleration would take. Exciting? You don't run into this a whole lot in mechanical engineering practice unless you're designing linkages that specifically have sliders on rotating links. If you do, then this is one of the things you need to take into account. And then also there's a 4-bar inverted crank slider problem on 376 that also, as you're reading through this chapter, which I hope you're all doing, in order to stay safe, of course, that you should at least take a look through. Okay. Moving along, I'm not going to work through an example problem on this because they're crazy. Acceleration analysis of the geared 5-bar linkage. We've looked at this in class just as far as what the equations look like for position and for velocity of a geared 5-bar link. Acceleration, same thing that we do with all of the others. We take the velocity equations, take the derivative, and then rearrange them. If we use the Euler identity, we get a very long string of calculations for both the real, or the x-axis component, and the imaginary, or y-axis. If we clean that up, this is what it looks like. I probably won't give that to you on a test, because I don't want to see you cry. All right, so kind of finishing up the topics we wanted to cover tonight. Just like with velocity, where we had that equation, v equals omega r. If we happen to know the omega of a rotating link, then we can take the distance from whatever we're calling fixed out to the point of interest and find its velocity, right? V is equal to omega r. In the same way, we can find the accelerations for any point around a linkage. Now, this is kind of the figure that you would see in your book for this. I really dislike these because they get kind of crazy. This first one, SaO2, if you're looking at it online, this is actually the crank. It's just a body. The second one, or labeled number 3, APB, this is the coupler. And the rocker is this body 4. The reason that your author likes to use these figures is he wants to point out different areas on this where you can calculate the accelerations. I think it obscures things a little bit. But the point is that once we have alpha and omega, as long as we have then its position from whatever we're calling the fixed link out to any point here, we can calculate the normal and tangential acceleration at those points, right? What's the equation for the normal acceleration? Yep, omega squared times the length. And somebody else, what's the formula for the tangential acceleration? Somebody else, sure. Thank you. So really, we can get that for anything on a linkage like this. Okay. And then I mentioned to you that I wanted you to do some reading to keep you safe over the weekend. This is for section 7.6 and 7.7. In particular, I think in section 7.6. Figures 7-10 and table 7-1. Those go through human tolerances for accelerations, and that's actually test data. So that's the kind of thing that somebody would have been looking at when trying to figure out, for instance, what an astronaut can take on launch, or what kinds of accelerations are acceptable in a crashing vehicle. Kind of neat stuff. And then jerk. Jerk is not me. Jerk is not any of you either. Jerk is the next derivative of the acceleration. What you find jerk being used in quite often are highly dynamic situations, because you're trying to figure out how the acceleration is changing, because that obviously has an effect on the force. Force is equal to mass times acceleration. If the acceleration is changing wildly, then those forces are changing wildly. You do see this used in a lot of cases in things like, let's see, machinery that stops and starts very quickly. You'll see it quite often, for instance, in high-speed machine tools. You'll see it used by engine designers because they want to know what's happening to the components in their engines. So it is something that you run across. And when somebody says jerk to you in 5 years, don't immediately assume that they're talking about you. Okay, any questions? All right, let's hand back the tests. For those of you online, please note, as I said, that there are comments on your Canvas sheet. You don't need to stay online now because I'm just handing back the physical test. Well, no, I guess I'll talk about it a little bit. Let me hand it back. Still learning names, so bear with me. Anthony.
Hi. You run this side.
Johnny. Caleb.
Caleb here and then Caleb.
Zach.
Lucas.
Lucas.
I'm here.
Max. Dylan. All right. So a couple words about the test. The average grade on the test was 81%. Not bad. Not bad. Per the normal sliding scale, that's a B minus. The first thing that I want to say is if you did not do as well on the test as you would like, please keep in mind 2 words. Don't panic. Okay? There will be opportunities to make that up. Our first one is the extra credit that we just talked about. Secondly, and I think I mentioned this in the first lecture, I do calculate your grade with all 4 tests, and then I look at it calculated with 3, dropping one of the first 3, whichever one's your lowest, and that will affect your grade. Because I figure everybody can have one off day. All right? As far as the problems, problem 1 was just a basic open, finding the position of mechanisms. Most people did pretty well with that. There were some people who had difficulty with a couple of the intermediate calculations. As we've seen, those really don't correspond to anything physical. Not easy to see what they are, so if you make a mistake, it's very difficult to figure out. That's why I strongly recommend, guys, that you get into the habit of drawing your figure. It doesn't have to be perfect, but if it's kind of, sort of where it should be, and you get an answer that's wildly off from it, that's a clue. Second problem. This one was finding omega 3 and omega 4. The angles and lengths were given to you. The only real problem was that some people had difficulty remembering where those angles are on the figures. That is something that you just have to get used to. Theta 2, 3, and 4 do correspond to specific locations on the figures. Problem 3, maximum and minimum transmission angles. This one, I always try and give at least one problem that's kind of just plug and chug, not too hard. This one I had a few people who had some difficulty with it. I think they were looking at it as finding the lengths for maximum and minimum transmission, but you were already given the lengths. We wanted to find those angles. And problem 4, this one was looking at the lengths potentially of L2, which is the shortest length because it's defined as a crank rocker. This one, more people got it wrong than I would like. I think they missed that it was a crank rocker. This is one reason why I'm making sure that there is an extra credit immediately after this test. One that hopefully is not too easy, not too difficult. If you have specific questions on any problem, you can either see me for a little bit right after class, or feel free to email me a picture of your problem, and we'll go over the actual solution individually, okay? All right. Everybody have a great night, great remainder of the week. I will post both that homework problem and the extra credit problem, so I remember what it was. Okay, we'll shut down the online. Let me know if you have any questions, guys.
I was wondering if, next week, it might end up working out better for me if I could not be on campus for class. Do you mind if we jump on?
No, I don't. An occasional thing is
Okay,
perfectly
cool. I
fine.
just